Okay, so Professor Yuan, it's all yours now.
Okay, thank you very much, Professor Fujiyoshi. Would you like to share your screen? Good evening, for those people from Japan, China, and Hong Kong, and good morning for people from Canada, in particular in Montreal, and for those people from Europe, good afternoon. So, welcome to the second day of the conference. So, same as yesterday, we will have two keynotes, one at the beginning, and will be given by Professor Fujiyoshi, and one at the end. So in between, we will have two very exciting technical sections. So today, I'm honored to introduce the first keynote, Professor Fujiyoshi. He got the PhD degree in electrical engineering from Shibu University in Japan in 1997, working on fingerprint verification using spectral analysis. After that, he moved to the US, CMU as a postdoc, and working on DARPA video surveillance and monitoring project. And then after that, he also worked in the Honda humanoid robots. Okay, and then returned back to Japan, and currently he is a professor in Department of Computer Science, Shibu University. So today the talk is talking about visualization direction of attention to understanding AI decision. So without further ado, please join us to welcome Professor Fujiyoshi. Please.
All right. Hello, everyone. My name is Hironobu Fujiyoshi, and I'm from Chiba University. Thank you very much for giving me this opportunity. I am so pleased to talk about the latest research related to the visual explanation of deep neural network. So as you know, deep learning has had a huge success in the area of image recognition, speech recognition, and language translation. I believe that the next step of deep learning for practical use is interpretive deep neural networks. Towards understanding and explaining the deep neural network, there are three main approaches: smooth flat analysis, sensitivity to input, and LIME, L-I-M-E, estimates the output trends for the various inputs, and CAM and GradCam outputs the attention map that is used for the visual explanation. So these are examples of attention map for the visual explanation. The top image is a goldfish, and attention map here highlights the discriminative image regions used for the image classification. Visualizing the attention map of failed recognition can help you to discover where the problem lies. For this example, there are lots of seeds in this image. When you input this image into the trained CNN, its output is misclassified as cow. Take a look at the attention map. You can see that it responds to the black sheep and white sheep. In fact, this is a problem called model bias. Actually, training samples were all white sheep and did not include black sheep. So this CNN didn't train the black sheep. Animals that contain the black and white patterns were misclassified as cow. So in this way, by visualizing the attention map, we can get an idea of the basis for the AI decisions and how to improve it. So how do we compute the attention map? The class activation mapping proposed by Zhou highlights the most informative image regions relevant to the predicted class. A global class activation mapping apply the global average pooling that computes the average of each feature map. In this case, this image is classified as the Australian Terrier. Then we compute the weighted sum of the feature map of the last convolution layer to obtain the class activation mapping as the attention map. So the class activation mapping is a good way to visualize the attention map by introducing the global average pooling. However, the global average pooling causes a decrease of the recognition rate because the global average pooling lost spatial information. To overcome this problem, we propose the attention branch network. We have presented this work at the CEPRAI 2019. So, attention branch network consists of three parts: feature extractor, attention branch, and perception branch. Feature extractor extracts the feature map by convolutions with a res block. Attention branch generates the attention map by global average pooling, almost same as class activation mapping. The perception branch outputs the classification results using the attention map. We train the attention branch and perception branch by end-to-end learning. For the inference of the attention branch network, we first compute the feature map by feature extractor and outputs the attention map by the attention branch. Then we multiply the feature map by attention map as an attention mechanism. The perception branch outputs the final classification results through the res block and FC layers. We evaluate our attention branch network with the ImageNet dataset for image classification task. In this evaluation, we use three typical networks: VGG, ResNet, and SENet, and compare the performance with and without the attention branch. In VGG, attention branch network improves the performance by 5% over vanilla VGG. In ResNet and SENet, the performance with the attention branch network was equal to or better than that without it. So next, we evaluate our attention branch network with a comprehensive car dataset for fine-grained image classification task. Here, this dataset contains 72 classes for car make and 431 classes for car model. For car make classification, attention branch network was 7% better than the vanilla ResNet. For car model classification, the attention branch network was 6% better than the vanilla ResNet here. So this is a visualization of CNN features before and after the attention mechanism here by TSNE. As you can see, there are few clusters of CNN features at the feature extractor. Each cluster contains the same pose of the vehicle, such as front, side, and rear like this. By introducing the attention mechanism, we see that distribution of the CNN feature with attention map is spread. To clarify the difference, we compute the distance between the CNN features. Blue color shows the distance for the same car model, and orange color shows the distance for the different one. From this, we see that the better CNN features for the classification can be obtained by the attention mechanism. So these are examples of the attention map for car model classification and car make classification. So as you can see, the attention map is different even though the test image is the same. Do you know this car? This is very famous in Japan called GTR. GTR has a characteristic of on the rear like this. So then for the car model classification, attention occurs on the rear side of the car. Our attention branch network can be easily extended to the multitask problem. So we generate the attention map by applying the attention branch to each task. Then the perception branch for each task uses the attention map correspond to the task, as shown in this figure. So these are examples of the attention map for the face attribute recognition. In the classification task for smiling, the circle indicates a positive classification. And we can see that attention map highlights the area around the mouth for the smiling. So the source code of our attention branch network is available on GitHub. So please feel free to use it if you are interested. Sometimes we want to adjust the deep neural network to output the correct answer. That makes sense, right? However, adjusting the network parameter is very hard because deep neural network have such a huge number of parameters. 61 million parameters on AlexNet, 140 million parameters on BGG, and 60 million parameters on ResNet. So I'm going to show you how to manually edit the attention map in order to output the correct answer without any changes in the network parameter. So here we have an attention branch network trained by the ImageNet dataset. The classification results of this image is suckable. Unfortunately, the ground truth of this image is Dalmatian. So how to fix that? So we first delete the unnecessary region from the attention map and add the region of interest like this figure. Next, we use the edited attention map to infer the network. Then the classification results will be a Dalmatian, which is the correct answer. So as you can see, it is possible to adjust the deep neural network to obtain the appropriate output by editing the attention map. So we developed the tool for the editing the attention map interactively like this. So first, by adding the region of interest on the cat area like this, then classification results changes from the basset to the tabby cat like this. So now we know the editing the attention map make it possible to adjust the deep neural network. So let's fine-tune the network using a manually edited attention map. The first step is to correct the attention map with incorrect answers, like this. Second step is editing the attention map manually by adding the region of interest and deleting the unnecessary regions. The third step is fine-tuning, retraining only the attention branch and perception branch to minimize this learning loss. So these examples show the effectiveness of fine-tuning. Here, these are attention map of ABN, Attention Branch Network. The top one is the correct answer, but attention occurs around the ground. The bottom one is the incorrect answer. Then we do a fine-tuning the ABN, Attention Branch Network, by using the edited attention map based on the verbal information as a human knowledge. These verbal information circles show the locations where humans make a correct answer. Therefore, the fine-tuned network can output the correct answer with a high confidence, as you can see here, and fine-tuning enables us to obtain the appropriate attention map. So this table shows the top one accuracy rate for the CUB 200 data set, which is 200 bird classes problem. So from this table, we can see that fine-tuned ABN, Attention Branch Network, is better than the one without fine-tuning for the fine-grade image recognition task. So these are another example of the attention map of before and after fine-tuning. Bubble circle shows the region of interest annotated by a human expert. We see that the attention map of the fine-tuned network is almost same as the region of interest annotated by the human expert. This makes to obtain the better visual explanation of deep neural network. We are now trying out our attention branch network for practical use. So let's look at the example in the medical field. Here, we trained the CNN that classified whether this fundus image includes disease or not from the labels annotated by the expert. So medical diagnosis is a task that requires explanation, not just the results of the disease or normal. So here, we perform the disease classification of the fundus image. So using the AlexNet, we had a 95% correct answer rate. The attention map of AlexNet by GradCam highlights the various areas like this. These images show the disease area annotated by the expert, showing this disease area different here. In another word, AlexNet, a conventional CNN, looked at the normal area and classified into the disease. So can you trust this AI-based diagnosis? I guess no. So by fine-tune the attention map based on the human knowledge, percentage of the correct answer will increase to the 99%. And you can see that the fine-tuned attention branch network highlights only the same area annotated by the expert. This demonstrates that our attention map is better for the visual explanation of disease classification. Actually, you can download the source code of the attention editor from the GitHub. So it is very fun for the understanding what's going on inside of the network model by editing the attention map interactively. Okay, let me move on to the topic of the self-driving car. NVIDIA's self-driving car is very exciting. In this car, CNN maps from the low pixel CNN maps the low pixel from the front-facing camera to steering command for the self-driving car with end-to-end running. After 3,000 miles training, actually, it works like this. So this CNN maps from the low pixel of the image to the steering command. That is very interesting. So I have a strong interest in NVIDIA's self-driving car. So we take the same approach as them, but using the simulator instead of real car. Specifically, we use the Grand Theft Auto 5 video game and collect the game screen, steering command, throttle command, and car velocity. We collect the data in a variety of the situations, including the country road on the sunny day, on the city road on the cloudy day, on the rainy days, and the night. We train the CNN to output the steering and throttle command from the low pixel and car velocity. Since the single image is not enough to control the car speed, so we connect the car speed of the car to the FC layers, so that network can output the appropriate throttle command. The video on the left shows the CNN controlling with the RGB image only. The right one shows with the RGB image and velocity. So as you can see, a single image and car velocity can control the car like this. This video shows an example of the downhill case. You see, it's hard to avoid the collision from the image only. On the other hand, with the car velocity, it is okay like this. Here, I have a question. So do you want to get in this self-driving car? My guess is no. Why? Because it is difficult for us to understand how system performs its judgment. So we introduce the attention branch to this. With attention branch, we use a weighted global average pooling and hyperbolic tangent to accommodate the regression task. We train the attention branch and the regression branch by end-to-end running. So this is an example of the attention map for steering command. Now it's steering to the left and then right. Positive value for the steering command means steering to the right here. In this case, attention occurs on the center line, so that we don't move out the lane. Negative value of the steering means steering to the left here. So we see that attention occurred along with the edges of the driving lane, opposite to the direction of steering. So the right one shows a visualization example by visual backprop, which is a conventional visualization method. I think our attention map is better for the explanation of steering control of the self-driving car. So this is an example of the attention map for throttle controlling. When the car stops, attention occurred here. So we can see that attention occurred around the brake lights of the front car to avoid a collision. This is my explanation based on the observation of the attention map, not a direct explanation of deep learning. However, it is clear that the attention map helps to explain how system makes its judgment. So can I ask a question again? So do you feel okay for getting this self-driving car now? If yes, so that's great. So now we are working on the language explanation by using the dense captioning. We select the appropriate captioning by attention map like this. So actually, this is an example of the language explanation when the self-driving car is braking. So I think this is just a first step. So there are three steps. I think there are three steps to be taken for us to accept AI-based service by deep learning. The attention map is the first step for the understanding what system recognizes. The second step is to understand how the system judges from the attention map and recognition results. The last step is going to be a language explanation. For self-driving car, we need to explain to passengers the reason for the system action by text, like a rear vehicle accelerates and approaches from the behind. So we are changing to the left lane like this. I also think this explanation function can eventually be turned off in the future due to the people learn to trust the AI. So this is summary of my attention branch network we have discussed today. And this work was done by my former student, Hiroshi Fukui, in a collaboration with my colleague, Tsubasa Hirakawa and Takayoshi Yamashita. This is the end of my talk. Thank you so much for listening.
Yeah, this is my talk, new DCT-FFT fusion-based method for caption and syntax classification in action video images. Actually, in this work, we have considered action video images. I think in last keynote speech also we have seen how to recognize action in the image. Of course, unless you have a video information and a temporal information, it is very difficult for us to detect action in the images. So in this work, actually, we don't consider video here. We consider only single frame or single image. So to classify the caption and syntax. But the motivation is something like this. Okay, if you want to identify the action in the image, without temporal information, without video information. So how it is possible? Yes, there are approaches. So they will follow some other maybe computer vision based and content based image retrieval in that way. But of course, since our background is a text detection and text detection recognition, so if there is a text in the image, then definitely we can make use of the text information to detect the action in the image. So that's what the point here, that's what the motivation here. So of course, if there is a text, automatically it gives a meaning of the content. So in this case, actually we consider now scene text and caption text. Caption text is actually edited text. Scene text is actually a part of the image. So scene text gives some kind of a context information, but caption text explains exactly the meaning of the video. So we need to differentiate these two texts so that we can combine meaningful information to detect the action or understand the video, understand the meaning in the image. Okay, that's our motivation here. So this is what my plan. So introduction, so motivation, of course I've already explained, then the proposed methodology, and finally we'll show some experimental results to validate our proposed methodology, and conclusion. Yeah, as I mentioned earlier, so recognizing action without temporal information is a tough job. That is actually motivation for our work. So when there is a text in the image, so definitely we can use the text information to identify or to recognize, to understand the content in the image. So, but the problem here is, so in one image you can see both caption and scene text. Of course, you know very well that scene text is different. The nature of the scene text and the characteristics of scene text is totally different from caption text. Captions text, it is actually edited text. Since it is edited text, we can see clearly, we can expect even a good clarity, we can expect a good contrast. But in case of a scene text, since it is a part of the image, it all depends on the image quality and the image content. So that means we cannot predict what is the nature of scene text here. So when single image contains two kinds of text, then it is very difficult for us to develop an algorithm to detect or recognize the text information. So of course, so in order to improve recognition performance, in order to enhance the recognition performance of both the text, so one way is to classify caption and scene text. So that is the idea here. So we have considered here actually 5 classes. So craft, yoga, recipe, and teleshopping, and concert. So just we have taken 5 classes here, action classes, so in which we can see, we'll try to look for caption text and scene text in each classes. So and that is our job here. So if we take in this class as input, and we'll try to see if there is a text, so we'll try to classify it. So whether this one is a caption or scene text, caption and scene text in each classes. Of course, our ultimate goal is, so somehow we need to improve the classification rate. So classification rate and recognition rate here. Of course, in this work we consider only recognition rate. So we'll try to improve the recognition rate of the text in this class, in this class, in this class, in this class. That is what our goal here. Okay. Now this is the motivation. Look at this one. Before classification, this is the recognition result with one latest existing method. So we can see a lot of errors here. But after classification, yes, we can expect good results. Yeah, this is possible because when you give a whole thing as an input, definitely complexity of the problem increases. So when you classify, that means when you have individual classes, then obviously the complexity of the problem reduces. So when the complexity of the problem reduces, definitely we can expect a good result here. That's the whole story here. Okay, now so our approach is something like this. See, our idea, our job is to classify caption and scene text here. So as I mentioned earlier, caption text is actually good text. So that means it's a good, you can expect a good clarity, good contrast. And of course, we can expect even uniform color also. So, but scene text, yes, we don't know the nature of the scene text. So it can be anything now. So this is the observation here. So that means caption text, definitely we can expect something good information, but in case of scene text, we cannot expect a good information. So this information, we are trying to use this information to differentiate caption and scene text. So for that, we try to propose DCT and FFT combinations here. Of course, you know very well that DCT definitely gives high frequency coefficients definitely represent an edge pixels, and similarly high frequency coefficients in FFT also represent an edge pixels. So we are trying to combine these two things. So then finally will fuse the image. When you fuse the image using these two coefficients, and of course, so then we will see what kind of features we should extract to differentiate a caption and scene text. So this is just in a simple equation. So we used actually variance as a weight here to fuse the images on DCT and FFT coefficients. So of course variance is a very good weight. This is actually very important. This plays a very important role here, because in case of a caption text, we can expect a uniform color. So when there is a uniform color, uniform values, definitely variance is less. Variance gives a very low value. When there is different values or abrupt values, definitely we can expect a high variance. So that is the reason we are trying to consider variance as a weight for fusing the images. So here, sample results here, sample illustrations, you can see caption and scene text. These are the two images. This is actually caption, this is a scene text here. So look at this is a Fourier transform of Fourier coefficients of caption and scene text here. And this is a DCT, and this is a fusion of DCT and Fourier coefficient. Okay, now try to understand here DCT coefficients, what happens here. So if it is a caption text, this is actually caption text. Look at this caption text, you can see it's scattered bright pixel here. But scene text, you can see at the end of this in a corner, actually left rightmost corner, we can see more brightness here and more darkness towards this end. This is the nature of, this is the property of the DCT coefficient. Of course, scene text actually, why this is happening? Scene text actually is the original text. That means it's the original text. But this caption text, actually what is happening, this is actually something like a tampered text, because it is an edited text. When you edit something over on video, definitely it is something like a tampered. So since it is a tampered, we can expect scattered coefficients here. So that means there is a difference here. So this is what the difference, this is what the observation here. Okay. Now we can go back to again we will try to reconstruct the image. This is actually reconstruction. So when you reconstruct this image, look at this one, what is happening. Of course, the quality changes here. So see, this is actually how we can visualize the quality changes in the fused images. Fused images or maybe reconstructed images here. See what is happening here. See, this is actually carry edges. Carry edges for the caption text. Caption text, no problem. We can see something edges here. We can see even structure also. But for scene text, we don't see anything. So that means we can expect some kind of a sparsity here for scene text, because scene text is not we cannot expect good clarity and good contrast. So definitely there are chances of losing information here. So that is the reason we just use simple condition here. The average sparsity is larger than non-sparsity. So that means you'll just count the number of pixels or number of components, and finally we define this as a sparsity and average sparsity. So for average sparsity is greater than non-average sparsity count, then we can say it is a caption text. So sparsity, that means in scene text, else it is a caption text. So I think that's all the simple work here. So we have considered some data for classification. So for validation, these are the sample images of our data set, caption and scene text data set, and the successful images. And this is the result, quantitative results of proposed and existing methods. See, this is the recipe. This is a concept for each class. We have calculated confusion matrix and average classification rate. This is a proposed method, and these two are existing methods. And of course, proposed method reports better results than existing methods for every classes. And this is actually standard data set. Of course, we have tested on even standard data set also. So for standard data set also, proposed method is better than existing methods. And finally, this is validation, recognition performance before and after classification. See, before classification, so this is the recognition rate with this method, and this is the one existing recognition method. So before classification, you can see results a little bit lower, and after classification, definitely caption and scene text, when you compare it to before classification, definitely recognition rate is higher than before classification rate. Similarly, with this recognition method, same thing we can we can draw same conclusion with this method also. So that means what we can conclude here, classification is definitely helps us to improve recognition performance. Okay, some limitation, definitely, of course, as I mentioned, scene text is very problematic for us. So we cannot expect what kind of nature of scene text. So definitely sometimes it will match with whatever you extract the features, it will overlap with the features of any caption text sometimes. So scene text, sometimes scene text misclassified as caption text, sometimes caption text misclassified as a scene text. Of course, when it is blur and when it is too much degradation and distortions, then also, yes, our algorithm not fails, but performance goes down. So this is a conclusion. So we have proposed something fusion method here. Of course, we fuse in both DCT and FFT coefficients, and then finally we calculated sparsity and non-sparsity count to classify caption and syntax. And finally, of course, then we have shown some recognition result to validate our proposed classification, whether classification improves recognition performance or not. And yeah, that's it. That's all of this talk. Yeah, and this is also a very interesting topic, a new method for detecting altered text and document images. That means we are trying to identify the forgery or tampered information in the document images. Here we take in a PDF document as input. So of course we use in a copy paste and insertion operation to make a forgery. So what is the approach? Let us see. Yeah, this is a plan of our work and presentation. And introduction, yes, introduction is, I think, yeah, there are a lot of applications for this, especially PDF document. And you take a PDF document, I have seen in many cases in India also, abroad also. So there are some cases where you can see some people try to change even a date and a date in the air ticket, or maybe name in the air ticket to enter airport. So you have seen many cases even in India also. Of course, other countries I don't know, but I have seen many cases in India. Similarly, we can expect even bank insurance documents and even property document, and even answer script evaluation and suicide note. Yeah, there are many cases like this. So where you can see some kind of an alters, especially even you can see some kind of a receipt also. So of course, when you change one digit in the receipt, so probably yes, it will make a disaster. So it will be problematic. It will be dangerous. So like this, you can expect in many applications for this problem. So this is one sample. So this is a copy paste operation. These are the lines we copy and pasted here. This is one kind of a forgery. This is another kind of forgery. We just inserted. So this text, these numbers. So these two operations we use for creating a forged data. So what is the approach? Again, we are trying to explore DCT coefficients here. So because we know very well that DCT coefficients, as I mentioned in the last talk also, so if it is a really original and genuine document, a genuine text, then we can expect in one corner high brightness, and slowly, gradually, the brightness decreases towards another end, another corner. So this property is very interesting for us to differentiate whether content is tampered or is a genuine or without any alteration. So that is what we are trying to explore here. So of course, Laplacian filtering is just to remove some kind of a noise information, and then finally quality features. That means we know very well that when you tamper something, yes, that is our assumption also. Of course, every forgery detection work assume that when you make some forgery, when you perform some forgery operation, it will introduce some kind of a distortion. So based on the distortions, so we'll try to identify or detect the forgery in the image. That's the whole story and that's the whole basis. But here, forgery, when you perform some forgery, definitely we can expect some kind of a distortions. Distortions are nothing but what? You are losing the quality and poor quality images. So that's the reason we brought in we extracted in quality features here. So that's also one kind of a feature vector. So and finally, so of course, just quality based features are not sufficient for achieving a good result. So we used even histogram bins. So anyway, just intensity values and other features. Okay. Now this is our approach here. So input is a forged document, and of course not only forged text information, we can give even genuine also, original also, and finally we extract DCT coefficients. So we try to divide DCT coefficients into positive and negative coefficients, and finally we fuse it. So fusion, and fusing is actually a simple operation we use in averaging or something. So here the idea is something like this. If it is a forgery document, if it is a forgery, what happens? So when you classify positive and negative coefficients, so because of the forgery, some of the positive coefficients is classified as a negative, some of the coefficients, some of the pixels which represent in the coefficients, so negative probably classified as a positive. So why? Because your content is tampered now. When content is tampered, so it is not genuine, definitely there are chances of misclassification here. So when you fuse misclassified coefficients, that means when you fuse using misclassified coefficients, definitely there will be a reflection, there will be a change in the fused image. So that is what the whole idea here. Okay, that is the basis here. So look at this illustration here. This is the original and altered. This is altered. This is the original image. So original text here. So it's a positive DCT coefficients and negative DCT coefficients, and this is 0. Look at this one. What is happening here? So this is actually original. So look at original. Look at this part. Look at this part here. This original. Yeah. look at more brightness here, and maybe a little bit when you move towards this end, so we can see some dark color here, 0 values. And here look at, there is a difference here. We cannot expect same pattern here. So that means we can see some observations, we can see some difference here, DCT giving in some difference here for original and altered images. And this is the reconstructed images for positive coefficients, and this is a reconstructed images using negative coefficients. And finally we just perform some Laplacian filtering to remove some kind of noise. And this is a positive and negative, and this is what a fused image. See, this is what the fused of original and altered images. Look at this one. When you fuse this one, definitely we can expect in brightness, more brightness here. This actually, we lost brightness here. So because this is actually tampered image, forged image, forged text information. So how we can visualize this one? Look at this one, canny. When you apply canny on these fused images, so canny, definitely we can see some kind of structures here, but here, yes, structures, we cannot even see the structure compared to this one. This is we can expect in a more unstructured, and we lost actually structure and even shape. So it is very difficult for us to, even from our eyes, it is very difficult to read the text information, but here at least we can read the information. So that means what I am saying, yes, when there is a altered, we can expect some kind of a disturbance, kind of a distortions here. But yes, again we used even Sobel also. Sobel also, it is true. See, Sobel is giving very good fine edges for this one original image, but for this one, yes, definitely we lost in structure and lost in information edges also. So this is what an observation here. So of course, then we try to calculate for what is this one? So quality measures. So, and of course quality measures is also one feature vector. And of course not only that, we try to extract the features like in histograms. Of course 25 bins, I think we have divided into 25 bins, and finally each bin is a one vector. So we combine all the vectors as a feature matrix, and finally even fused images also we perform histograms. Look at the histograms, definitely there is a difference here. So this is the original, this is this one, we lost information here. Here also same thing, you can expect some difference here. And similarly, this is actually residual. This is the difference between fused and input here, input image. And look at, see, this is totally, we can expect some different shape of the histogram. That means in distribution. So that is what we wanted. And finally we pass everything to CNN classifier. So CNN here to classify the things. So that's the whole our approach. Now we have used our own data set also. And of course this is actually benchmark data set is there. This is actually a receipt, which data set again gives in receipt information. So of course we can see original receipt also and forged receipt also. Receipt means here we can see only numerals and numerical values. So and of course one more benchmark data set is also, we have used one more data set. This is actually images of an IME number. So this is a mobile unique number, identity number. So that's also one, there is one data set. So we have used in a 2 standard data set for testing our methodology. And this is what in sample images of our data set. And this is standard data set, receipt information. Look at the, this is original and this is altered. We can notice here, easily we can notice some distortions here because of the forgery. So, and this is another data set. And finally, so this is actually something in ablation study. Quality measures, what is the accuracy, what is the classification rate and average classification rate and the confusion matrix also. Only fused image, only residual, and difference between histograms, and finally proposed method. So I think every step is contributing and every step is effective to achieve the final results of proposed method. And this is one methods and the proposed method. This is classification rate and the confusion matrix of the proposed method. Okay, so our data set and this is a standard data set and one more receipt forgery data set. And these are the existing methods, and of course proposed method is better than existing methods here also for all 3 data set. And of course some limitations are there. Definitely, yes, forgery operation sometimes operation is does not introduce distortion, then of course our algorithm fails here. So whole algorithm depends on the distortions introduced by operations. If operation does not introduce enough certain amount of distortion, then obviously we lose any features. Yes, the conclusion. So we have proposed here, actually, main contribution here is exploring the DCT coefficients. Of course, we try to divide positive and negative coefficients, and then finally we fuse it. So that is an interesting property here. And then, of course, we extract quality features, quality measures as a feature extraction, and finally we perform some histograms to extract the features. Of course, finally we feed all the features, feature matrix to CNN classifier, so to classify the things. So yeah, thank you. That's all from my side.
Thank you very much. And so Yufang Tang will present commodity classification based on multimodal jointly using image and text information.
Hi everyone. I'm Yufang Tang. I am postdoctor in Concordia University. My supervisor is Professor Ching Suen. My paper title is Commodity Classification based on multimodal, jointly using image and text information. There are 4 sections I want to introduce. First, I want to introduce the background of my paper. We know that there exists image and text information almost on every web page, especially on the commodity web page such as Amazon and Taobao. And the image and text information belong to different models, but because they describe the same object, so there must be a certain relationship between them. Based on the above fact, we proposed our method for commodity classification. This is the structure of our method. From the website, we can get the image and the text. Then we use 2 different classifiers to get the image classification confidence and the text classification confidence. Then we use a fusion classifier to classify the commodity. There are 3 key issues in our method. The first one is how to get the image classification confidence. The second one is how to get the text classification confidence. The last one is how to fuse the 2 different model classification confidence together. Let's see the first one. For this question, we proposed a solution, optimizing sparse representation algorithm for image classification, where delta 2 and 0 mixed norm. The equation 1 is our model. In our model, there are 2 important questions should to be solved. The first one is how to learn the dictionary D. The second one is how to solve the sparse representation alpha. Alpha is the sparse representation of the commodity image. The 2 important questions, you can find the detail in our paper 1 and our paper 2. When we use the equation 4, we can get the residual image E. Then we can use the equation 5 to get the image classification confidence. Now we have solved the first question. Let's see the second question. For this question, we proposed a solution, optimizing key nearest neighborhood for text classification, where Bayesian posterior probability. We know that for the traditional KNN algorithm, the equation 6, equation 7, and the equation 8 is a mathematical model. But there are 2 very important problems in traditional KNN algorithm. The first one is that it uses observed frequency as a contribute degree of word for the text classification. But this method causes high frequency words to submerge low frequency word. The second one is that in the training data set, if the number of the sample is unbalanced, this will lead to the bad result for the classification. In order to solve this two above problem, we proposed a method. We name it weighted Bayesian key nearest neighborhood algorithm. The idea of the method is that we use relative frequency to instead of the observed frequency. The equation 9 is a model how to calculate the relative frequency. Then we can use equation 10 and to calculate the posterior probability. You can see the details in the equation 11. Then we can calculate the text classification confidence, use equation 12. Now we get two different classification confidence, image classification confidence and text classification confidence now. The last question is how to fill the two different model classification confidence together. For this question, we proposed a solution. We know that the equation 13 and 14 is a traditional fusion classification method. So we use our model, such as equation 14, to fill the two different classification confidence. The details can be seen in equation 16. In equation 16, the two different classification confidence and come from the two different physical quantities, so they can't be fused directly. For this question, we proposed a method. Is that to normalize them? It's shown in the equation 17. So now we get the fused classification confidence. Then we can use the equation 18 to classify the commodity. Now I introduced my experiments. In my experiments, we used the two data sets, Small and IT. Small is an open source data set. There are only commodity images. Because we want to use both image and text, so we create our own data set. We name it IT. I stand for image, T stand for text. We did 3 experiments. For the first experiment, we only use the image for classification. We can see that in the two different data sets, our method SRC delta 2 and 0 is the best one compared to other method. And the other method is based on sparse representation. This is the details for different method in the image classification for every categories. This is SRC, this is CRC, LRC, this is our method. We can see that for every category classification, our method is the best one. This is the second experiment. In this experiment, we only use text information. We compared our method to the traditional KNN. We can see that even for the different number of the neighborhood, our method is almost better than the traditional KNN. In the third experiment, we use both image and text information for the classification. And our method, MMIT, is the best one compared to other methods. This is the details information about the experiments. We can see that for each category classification, our method can achieve a better accuracy. The average accuracy is about 95%. So we can see that our method can achieve a higher accuracy for the commodity classification. And meanwhile, we can use this method to other applications, and such as dating application. If somebody want to find people who want to date, they can use the text and the picture of the people. Meanwhile, we can use our method to many applications, such as recommendation system. That's all. Thank you.
So now the next presenter is Li Tuan Nam. He will present the paper Hand-Drawn Object Detection for Scoring Word-Tag-Zeichenn Test.
Good afternoon, everyone. I could now to talk about my work for hand-drawn object detection for scoring word-tag-Zeichenn test. This is the outline of my presentation. First, I will talk about the introduction. The word-tag-Zeichenn test is a method of personality evaluation developed by Eric Word-tag. The WZT form consists of an A4 size paper with 8 y square in 2 rounds. X square has a simple printed size as a dot or a line. The test person is required to make a complete drawing using the printed size as the starting point of the drawing, and then give a short explanation or title of each drawing. Chrissy et al. Introduced 3 new scoring category of the WZT. This consists of evocative character, form quality, and affective quality. The AQ is simple, the assessment of the emotional connotation of each drawing, and scored based on the object content of each drawing. The object detection method, object detection is one of the most basic and important tasks in the field of computer vision. Deep neural network-based object detection method usually can be divided into 2 categories. The one-stage method, such as Jono, directly classify the predefined angle, and further refining, then using DNN without the proposal generation step. The method usually achieve a high inference speed. The 2-stage method, such as RCNN family model, first generate a set of reason proposal, and then define them by DNN. These methods usually achieve high accuracy. Next, I will talk about the dataset. The CENPARMI WZT dataset is a dataset of WZT produced by CENPARMI Concordia University. This dataset consists of 2 sub-datasets, CENPARMI WZT PEP dataset and CENPARMI WZT square box dataset. The CENPARMI WZT PEP dataset consists of 211 scan WZT page collected from the test people. And this is some page example. The CENPARMI WZT square box dataset consists of 1,600 hand-drawn square boxes, and that were cropped from the scanned WZT page. The sketchy dataset is the first large-scale collection of sketch photo per dataset, which span 125 categories and consists of about 12,000 unique photographs and 75,000 human sketches. In this work, we employ the human sketches of the sketchy dataset to train the hand-drawn object detector. Next, I will talk about a little bit the Jono model. Jono is an object detection framework proposed by George et al. Jono is the first one-stage object detector based on DNA, which reframe object detection as a regression problem. Jono split an input image into an S grid, where each grid cell predict the bounding box confidence for the box and C-class probability. Jono can process image in real time with a better result than other real-time model. Jono version 2 is an improved version of Jono, which adopt several improvements, such as a convolutional layer with anchor boxes. Jono version 3 is the latest version of the Jono, which has a few incremental improvement on Jono. Jono version 2. Next, I will talk about the experiment. In this work, we conduct 2 experiments of the Jono version 3 model to assist in scoring the effective quality of WZT. The first one is hand-drawn square box detection. We use the CENPARMI WZT dataset to training and testing the model. The second one is hand-drawn object detection. We use the sketchy dataset to train and validate, and the CENPARMI WZT square box dataset to test the model. This table shows the MIP recall and precision of Jono version 3 on the test set of the CENPARMI WZT dataset. You can see the Jono version 3 with the IOU threshold of 0.8 achieve 88.94% of MIP on the test set. This result implies that the Jono version 3 can assist the detecting WZT square box. There are some examples of the hand-drawn square box detection result. This table shows the MIP recall and precision of Jono version 3 on the test set of the CENPARMI WZT square box dataset with 46.90% of MIP on the WZT square box dataset. Jono version 3 can assist the detecting hand draw object in scoring the AQ of WZT. There are some examples of hand draw object detection result. Next, I will talk about the conclusion. For conclusion, the hand draw square box detector by YOLO version 3 achieved 88.94% of MIP, and the hand draw object detector by YOLO version 3 achieved 46.90% of MIP, and this shows that the object detection method can assist in scoring the effective quality of WZT for future work. I will expand the model to detect the multiple objects as well as more object categories, and I also will collect more the WZT page image to improve the performance. That's all for my presentation. Thank you very much for your attention.
So we'll go on to the next session, session D, which is deep learning. And our first presenter will be Mohammed Tayeb Shalali. He'll be presenting from pixels to random walk-based segments for image time series deep classification. You may begin.
Good morning, everyone. Good afternoon. Today I will present you our study entitled From Pixel to Random Walk-Based Segments for Image Time Series Deep Classification. And the context of our study is focused on satellite image time series data, which is represented in 2D plus T spaces. And these large quantities of data allow us to monitor our planets. And it can be used to map our land use or manage our territories and also change detection. And we see in this figure that the administration of this data and each pixels have a temporal evolution. And we are going to label this temporal pixels. And our objective is the classification of agricultural crop field, not only a temporal pixel, but crop field based on this satellite image time series. And the challenge is how to deal with spatial and temporal domain during the analysis, and also what is the impact of low spatial resolution and high temporal resolution. Existing methods for satellite image time series analysis are different. They are that consider a pixel as a time series, then use a random forest or K-means in order to classify them. Others use a dynamic time warping, which is a distance that allows us to analyze the temporal alignment between two pixels, as we see in figure A. And there are also a recurrence closed method, which it starts by transforming time series into a 2D images, then the use of a 2D CNN to classify these images. And some classical deep neural network methods, we know LSTM, which is kind of a recurrent neural network, and we have also TAM-CNN, which is represented here. We see that the convolution are applied only on the temporal domain. Some research includes spatial information by extracting some handcrafted features computed at region level, as we see in the figure C. These features can be morphological, geometrical, or the mean of colossal. And these features can be combined with time series. And after, we will use K-means or KNN to classify this unreached time series. We have also a hybrid strategy where they use a 2D CNN in order to learn spatial features. And in other side, we use a 1D CNN to learn only temporal features. And then, as we see in the Fujiyoshi, the combination or the concatenation of these learned features allow us to consider both of spatial and temporal domain. And for image sequence analysis, we have a 3D histogram of gradient, mainly used for video classification, or we have also 3D CNNs, but this kind of models require a large dataset in order to fix all the parameters. We pass now to the proposed approach, where this approach starts by transforming the input, which is a satellite image time series, into a 2D images, as you see here. Then we will train a 2D CNN to label these 2D images. So when we say that we will pass from 2D plus T domain into only 2D, it means that we will reduce the complexity of the data structure. And the advantage of this is the use of 2D CNN and also benefit from pre-trained models, such as trained on ImageNet dataset. And the question is how we will include the spatial information. For this, we propose the use of random walk entities, as we see in this image, where this random walk will have a limited length. Here it is L. Then following the segment, we will line this pixel into 1D string, 1D vector, sorry. And we will repeat this process for all the images through the time. Then we will combine or stack all these strings vertically. And here we obtained our spatio-temporal representation. The spatial will figure on the columns of the image, and the temporal is on the rows. And when we take on all the column, here we say we take temporal pixels. In this image, we see an example of the spatio-temporal representation. These examples are obtained by the yellow segment that pass through this row. And in B, we see the high resolution image taken from Google Earth image. In E, we see the original size of this satellite image time series. And we compare here that the law of spatial resolution. Here we see that the yellow segment pass through the forest. And here we see that the forest have the same temporal evolution. Then it passes through a urban area. Here we see that the urban area doesn't affected by the temporal evolution. Then we pass through two types of meadows. Here we see the first meadows, it is on red. Here we see that and we see that these meadows start growing earlier, which is not the case for the second meadows here. We see that it doesn't start growing earlier. For the decision strategies, here we start by extracting a crop field, then getting different spatio-temporal representation based on different random walk segments. So why we do this? In order to consider different spatial configuration. Then we will classify each of these images, and finally we aggregate all the token decisions in order to take a unique decision for the crop field. We pass now to our experimental study. The used materials are a satellite image time series provided by Sentinel-2, censored in 2017. We have 15 images, and we notice that we apply a linear interpolation or unmasked zone by clouds. We see here the different spatio-temporal representation. and we consider different length L. And we have another strategy by designing to fill all the black, temporal black color here. And we do this by considering that in 1 year we have 224 dates. And by applying the linear interpolation, we generate false images in order to fill all the black color. We see here the number of instances for each class. Here we consider two classes, the intensive and the traditional or cards. Our experimentation are validated by using cross-validation techniques. We consider 5 runs. The used convolutional neural network is QuizNet. Why SqueezeNet? Because it has 50 times parameters, lower parameters than AlexNet, but it is still at the same precision when classifying at ImageNet dataset. We see here the quantitative obtained scores. So when we consider only 50 dates, we see that by training the model from scratch, we have 86 of accuracy. But when we use a fine-tuning technique, all scores are increased. And we see here the scan strategy, it is a naive strategy by when we take the segments horizontally and vertically only. And it is the worst strategy because the spatial configuration is not more important compared to the random walk strategy. And for the comparison purpose, we compare our strategy to Tang where the convolution are applied only on the temporal domain. And we see that all our scores are better than those of Tang. And when we consider the interpolated, or when we have 224 dates, we see that when we train our model from scratch or with fine-tuning technique, we outperform the temporal CNN strategy. To conclude, we propose here a novel spatio-temporal representation for image time series that is used to, 1, learn spatio-temporal features with only 2D convolutional neural network, and also used to classify this image time series. And we also benefit from a pre-trained model such as trained on imaged dataset. In our perspective, we will analyze the impact of the number of segments per polygon, because here we fix it only to 13. We will also use the class activation maps as presented in the Keynote with our planar representation in order to show which region of the image are more discriminant for the classification. We will also increase the number of classes leading to line the cover map, and trying to apply the method on other kind of image time series. Thank you.
Hello everyone. My topic is incorporating human views into unsupervised deep transfer learning for remote sensing image retrieval. Our study is based on our previous work. In reference 9, we propose a model called SBSCNN and applied the model to content-based remote sensing image retrieval. It's an unsupervised transfer learning model, and the knowledge is transferred from ImageNet to the unlabeled remote sensing datasets. This is the network architecture. The model includes two identical feature learning branches. They aim for feature learning. And there is also a similarity learning network. It aims to learn the similarity between two images. And this is the output layer. The ground truths are some pseudo labels. The pseudo labels are similarity labels determined by image similarity. 5 CNN experts compute image similarity and provide the basis for unsupervised training. The details of how the experts compute image similarity can be found in reference 9. In SBS-CNN, how similar two images are is determined by CNN experts. We would like to know if CNN experts' opinion on image similarity is the same as humans. And besides, we also would like to know if human opinion can help to increase a CBRSIR system's performance. So, in this study, we propose to incorporate human views about image similarity into training process to improve the existing SBS-CNN. In this way, we collected human views. We use 10 grades to indicate how similar people think two images are. An app is developed and used to capture some people's views about similarities. Remote sensing images are presented in triplets, and people are asked to grade two image pairs in each triplet. For example, suppose the image triplet is XYZ. Then the similarities grades for image pairs XY and XZ will be provided and recorded. $15,000 different image triplets are assigned to 1,000 people, and each person is asked to grade 100 image pairs. Because each triplet includes 2 image pairs. And in this way, we incorporate human views into SBS-CNN. We let data be the difference between the grades of two image paths xy and xj. Then we define the grade triplet loss as follows, like this one. The formula 2. And we would like to emphasize A and B are both greater than 0. An adaptive purpose mechanism is introduced into GT loss through G data. How hard image paths are pulled depends on data, which in turn is determined by humans. In this way, human views about visual affinities among images is implanted into CNNs. Then we define WWO GT loss as follows. Like this one. Please see the formula 4. We call the new model ISBS-CNN. This is the network architecture. The inputs to the new model are image triplets. Now, let's see the experimental results. We conducted the experiment on pattern net. It's an area images set. First, we investigate if CNN experts' opinion on image similarity is the same as humans. In this graph, the green line means human, and the red line means Google Net. Second, we investigate if humans' opinion can help to increase a CBRSIR system's performance. In the first column, a smaller value means a better performance, and in the second column, a large value means a better performance. We can see that our model ISBS-CNN performs best. We reach two conclusions. First, the pre-trained CNNs and humans hold different views on image similarity. However, two kinds of views are strongly correlated. Second, human views can greatly enhance a CBRSIR system in terms of retrieval performance. That's all. Thank you.
This presentation is entitled Deep Active Learning with Simulated Rationals for Text Classification by authors Paul Gelorget, Titus Zaria, and Bruno Grière from Airbus Defence and Space, Télécom Sud Paris, and Institut Polytechnique de Paris in France. Before anything, I'd like to thank fellow organizers for their hard work and perseverance letting these events happen. First, we will have a short introduction for introducing learning with rationals, active learning, and text classification. Then we will develop on our contributions regarding simulated rationals and transfer of such rationals for text classification. Then some experimental results. So first, what is learning with rationals? Deep neural networks have shown exceptional results, state-of-the-art results, and very great generalization capacity when they are trained on a very large set of labeled data. However, some tasks don't have a very large set of training data, and the network lack generalization capacity. So learning with rationals is giving a hint to the networks about where the salient regions of the documents are. What are the regions responsible for class membership in a specific document? There is a setting where labeled data is especially scarce. It is early active learning. Active learning is a method used to tackle the lack of labeled data by having most of the time human oracle experts to label unknown documents. Active learning with rationals is the same thing, but the oracle not only provides labels for the sample documents, also they provide the rationals, that is to say the regions of interest in the documents that are responsible for class membership. And we want the model to take these rationals into account when it is trained. There are many text classification methods available. However, recent efforts in deep learning in the deep learning field have shown to be especially effective, relying on pre-trained word embeddings such as glove, fast text, or contextualized word embeddings like Elmo or BERT. And on top of that, we plug usually some convolutional neural network or some recurrent neural networks. The former has the advantage of preserving spatiality, the order of the representation of the input words during the processing of the sentence. So our contributions in this paper are concerned deep learning with rationals for text classification. For our experiments, we need some labeling tasks for labels first and for rationals second. Providing rationals for every document is quite tedious, so there is a need for us to simulate these rationals. So our first contribution consists in generating simulated rationals. Well-known method class activation mapping allow to produce heat maps of what regions of an image is responsible for class membership. What region of an image most contains the features, the high-level visual features that are specific to an output class. So this technique was usually introduced for image classification on convolutional networks. So we adapted this method on convolutional model dedicated to text classification. So this is the same principle, except here it is a one-dimensional convolutional layer processing word embeddings. And we obtain, for each class available, a heat map, or one-dimensional heat map of word importance regarding each available label. This is what class activation maps for text classification looks like, and something is quite striking. We want to simulate rationals that could have been produced by a human labeler. However, this is far too comprehensive and dense to be generated by a human. So we want to modify it so it can resemble what a human could have produced. So what we did is we did some pruning with some thresholding. We kept some percentage of the highest class activation mass values across the dataset. We used top 10, 3, and 1% values of the count across the dataset, and we binarized these thresholded class activation maps to have these more human-like rationals. On this example, this is film reviews, and we want to predict whether they are positive or negative film reviews. So here, for example, by selectioning a 1% threshold, this is the simulated rational we have to justify that this text, this review, is negative. So we have first, on the one hand, dense comprehensive class activation maps. In red, negative values, green, positive values. This is a negative review. And we have several levels of pruning. And what we see is if we prune too much, we lose everything. But this is possible. We can imagine a human oracle providing 0 rational for a text. This is possible, so we kept it that way. And here we can see at the bottom groups of words, 5 grams of words. What we did is with the first teacher model, we used the knowledge transfer appellations, namings. So a teacher model is trained on a very large set of documents, and our simulated rationals are extracted from all these documents. Then, during the active learning iterations, instead of a human, we use these simulated rationals to be injected in the active learning framework. To take these rationals into account during training, there are 2 methods that we have proposed. First one concerns our comprehensive, dense spatial knowledge. So we used L2 norm, mean squared error loss, to take them into account, in addition to regular classification loss. And regarding our more human-like rationals, we use this custom loss function. Now some experimental results. On the left, results concerning Internet Movie Database dataset, which is a dataset with positive and negative reviews, and the task is predicting whether the review is positive or negative. And the right-hand figure is about Windows versus hardware. The task is predicting whether the text is about Windows, so software or hardware. First observation is that transferring the dense, comprehensive class activation maps yields very good results, even with only 10 training documents as input. But as we said, we cannot expect a human oracle to provide such comprehensive rationals. So with our pruned human-like rationals that are red, pink, and blue curves, we still obtain better results than without taking the rationals into account at all. We believe that our method is beneficial for trainings with very low amounts of textual label data. Thank you very much.
Hello everyone, my name is Zahra Taleb, and today I want to talk about detection and recognition of license plates by convolutional neural networks. The goal of this work is developing a CNN-based approach for detecting, localizing, and recognizing license plates from real-world images and also the videos. The next goal is evaluating the impact of different activation functions on LPR systems. As you know, there are many different applications for license plate recognition, but they do not work for all types of vehicles, styles, and fonts, and they still have problems with different scenarios. Developing an automatic license plate recognition system with high accuracy and high speed from low resolution or still picture is still a challenging task among researchers. The challenges that we had in this work was the low quality, blur, uneven illumination, as well as various types of font and different color, direction, and complex background on the license plates. We used 3 different convolutional neural networks to introduce a system which can detect several license plates in a real-world images and is able to detect all types of vehicles. Our system has 3 main steps, as I told you: a vehicle detection using YOLO version 2, a license plate detection, and character recognition using OCRNet. For the pre-processing the image, the size of input images resized to 416 in 416 pixels due to the higher speed and accuracy in comparison with other dimensions. The proposed architecture has a total of 30 convolutional neural networks, and the size of all convolutional filters varied from 32 to 1024. For the activation function parts, we use Leaky and ReLU through the network, except in the detection part, which is the linear one, to detecting different types of vehicles. For dataset, we use UFPR, ALPR, and OpenALPR, which they are open source datasets, and also we use the CENPARMI dataset, which consists of 440 images of different pictures from license plates in Quebec, United States, and China. The WPON network was produced using computer vision methods like YOLO, single-shot multi-box detector, and a spatial transformer network. In the beginning, the network is fed by the resized output of the vehicle detection section, the feed-forwarding outcome in 8 channels features map that encodes object or non-object probabilities, then affine transformation parameters. To extract the warped license plate, imagine a square around the license plate, and the center of the square is the center of the license plate. If the object possibility for this cell is higher than the given detection threshold, then part of the regressed parameters is applied to make an affine matrix that transforms the imaginary square in the license plate area. Therefore, the license plate can simply unwarp toward a horizontally and vertically aligned object. The dataset that we used for license plate detection and rectification is the CAR, SSIG, and ALOP, which we did some data augmentation on the pictures, such as rotating, mirroring, scaling, and cropping. Most challenges that we have in the character recognition was the different font size, background, and foreground colors, dynamic length from 2 to 7 characters, and different order of numbers and letters in different license plates, such as Brazilian, European, Canadian, and United States license plates. The dataset that we use for the character recognition is UFPR, ALPR, CENPARMI, and OpenALPR. We chose some different vehicle detection threshold to finding the better threshold for our system. And as you see here in 0.45, we have the less undetected vehicle and also the less false positives. Also for character recognition, we have some experiments on different thresholds. And finally, we decided to stop with the 0.4. Here I want to show you some impacts of different activation functions. For the YOLO, you know that all the layers are leaky, but we try to change the activation functions just to see what will happen. And then we realized that the combination of leaky and ReLU would work better in comparison with other activation functions. As you see here, there are some results of our system, which is a license plate attached to a truck that our system could find all the characters correctly, even when there is a rectangular sign in the street and there are some text at the back of the truck. Here we have a license plate with complex background, and also the foreground is hard to read, but the system could find all the characters correctly. Some difficult pictures, such as this picture, as you see, the system could just recognize 3 of the vehicles correctly. There is a high reflection of light on this license plate, and our system could find 5 characters out of 6 correctly. Most of the commercial applications couldn't find this license plate. Here I have a comparison between our application and other commercial applications. As you see, our work performs better than the other license plate applications. I have some example of some pictures from different applications. This is the output of the plate recognizer, and here we have output from OpenALPR. And as you see, for this license plate, the plate recognizer couldn't find X, and here instead of X, the OpenALPR find 1, but our system find all the characters correctly. In this slide, as you see, for the 4 vehicles, both systems have problem with recognizing the license plate correctly. Here we have 22 HMJ, and here we have P22 HMJ. And as you see, the license plate number is P32. And here our system could find it perfectly. For the future work, we want to train our model to recognize some other license plate around the world. I mean, the Arabic version, maybe Indian characters, as well as Chinese characters, and enable the system to classify more than 35 Latin characters. And also, we want to develop an application for mobile phones, which the people could easily use this license plate recognition in the real world. And thank you very much for your time and your consideration.
Ladies and gentlemen, I'm very pleased to introduce our keynote speaker, Professor Changlin Liu, who is the director of the National Lab of Pattern Recognition of the Institute of Automation, Chinese Academy of Sciences. He has visited various labs in Korea and Japan, especially Hitachi lab. And I noticed that Dr. Hironiki Fujisawa is watching. And very glad, Dr. Fujisawa, you are here. And Professor Liu is also the Associate Editor-in-Chief of Pattern Recognition Journal and also Associate Editor of other journals. He is a Fellow of the Institute of, it should be called International Association for Pattern Recognition, and also of the ICPRAI. So welcome, Professor Liu.
So thank you very much, Professor Suen, for your introduction. So thanks for your inviting me to give a talk at the ICPRAI. It's my great honor. So for this time, I'm to share some of my work and thoughts on document analysis and recognition. So this is a very important application problem of pattern recognition technology. So I will first briefly introduce the background of document image analysis and the recognition, and give a brief history and introduce the major methods for the pipeline of document analysis and recognition and the state of the art, and finally show some of the new trends and identify some future directions of research. So document image analysis and recognition, in brief, document analysis is the main task in document analysis to locate and recognize the text in images, to convert the text from image to digital code so that the semantic information in image can be understood by computers. It has wide applications in paper documents, digitization, human-machine interaction, scene understanding, and information retrieval. So here is an example. In this image, there are some texts by handwritten or printed. So the first step is to localize the text regions, and then by recognition, the texts are converted to digital codes. Document analysis is very useful because document images are very prevalent in physical space and also on the web. So they include printed documents and handwritten documents and natural scene images, and also many bonded images. So the technology can be used in many different scenarios, since there are a huge number of paper documents and also text images on the web, and also the document images can be generated by handwriting online using touch pen, for example. And the technology is needed when we want to convert the text from image to computers and extract semantic information from the images. The typical pipeline of document analysis systems, first, after data acquisition, the first step is layout analysis. So this is to segment the text regions. And the next step is text recognition, also called character string recognition. So this is core step of document analysis. And in traditional pipeline, so that text line is first segmented into characters, and the character images are recognized, and finally, so language model is used in post-processing. But nowadays, a more common procedure is to recognize the whole text line, so even without word segmentation. so to convert the text line image into digital text directly. So this is a brief history of the document analysis research. Actually, as early as in 1920s, so there were first attempt of optical character recognition by optical template matching, and from 1950s starts the modern age of computer pattern recognition, and approaches of statistical pattern recognition, structural pattern recognition, neural networks, and deep learning have been tried, and many approaches have been proposed. Another target of character recognition was started from individual characters and then extended to word recognition and text line recognition, and now even full-page recognition has been attempted. So we can see that actually in the recent 10 years, actually the development of internet and especially the mobile internet has been pushed forward the area of character recognition and document analysis significantly. So let's see what are the major methods for the document analysis systems. For the steps of image pre-processing, layout analysis, syntax detection, text recognition, and end-to-end recognition. In image pre-processing, actually the traditional approaches will aim to improve the image quality using some morphological operations or using Markov random field. And many approaches of deep learning have also been proposed. And for binarization, so binarization is a very important step in traditional document analysis systems. So this is to separate the text from the background so that the noise background can be eliminated, and the processing of character segmentation and recognition can become much more simple. And so nowadays, pixel classification approaches have been proposed, including the Markov random field and conditional random field. And recently, the fully convolutional network has been shown to be very effective for pixel classification-based image processing and enhancement. And for distorted document images, many rectification approaches have been proposed. So layout analysis is a very important step. So this is to segment the text regions and also graphic regions in the document images. The main tasks are the page segmentation, also called geometric layout analysis, and layout understanding, or called logical layout analysis. Page segmentation has been studied intensively, but the problem is still not solved yet. But layout understanding is also drawing increasing attention in recent years. So let's see why page segmentation is very difficult, because the layout of document images are highly variable and many complicated. So many different elements, and both printed text and handwritten text are mixed. And many document images has a serious distortion. The traditional methods of page segmentation can be grouped into top-down approaches and bottom-up approaches. Like the recursive XY cut is a typical example of top-down approach, and Dockstrom and Voronoi diagram are typical examples of bottom-up approaches. So bottom-up approach is more flexible to deal with rotated and distorted document images, because local elements like connected components are first detected and then grouped into text lines and text regions. And in recent years, many approaches have been proposed to handle more variable complex layouts. So this includes deformable models, graph-based clustering, structured prediction approaches such as conditional random field and full convolutional network. Syntax detection can be viewed as a special case of layout analysis, since the aim is to locate the text regions. So this problem has been very popular from 2011, and the target of text detection has been extended from horizontal text lines to multi-oriented text lines, and very recently the aperture shaped text detection has drawn increasing attention. The tasks include text detection, text recognition, and end-to-end recognition, also called text spotting. Methods of text detection can be categorized into character-based approach and word or line-based approach. The character-based approach is to first localize the character regions or local regions, and then group the local regions into text lines. And approaches both based on traditional hand-grafted features or deep neural networks have been proposed. And word or line-based detection approach can be viewed as top-down approach. So this approach has been inspired by generic object detection approach. So it is to localize the whole text line or word directly. A typical example is a deep direct regression approach. And in recent years, the detection of aperture shaped text or curved text lines has been popular. So the bottom-up approach or character-based approach is more suitable for this problem, because the character shape is somewhat independent of the text line shape. So first, the character regions are located and then grouped into whatever shape of text line. So the text snake was an early attempt to detect aperture shaped text lines. And this approach, called aperture shaped text detection, is to use a recurrent neural network to detect the aperture shape boundary fitted by arbitrary number of vertex points. So it can be viewed as a top-down approach because it detects the whole text shape directly. So the recent approach called deep relational reasoning graph network is to first localize the character regions and then analyze the relationship between the characters and to group the characters into text lines. Because it used a graph convolution neural network, so it can handle arbitrary text line shape. In text recognition, of course, is the most important step in document analysis, because the objective of document analysis is to convert the text from image to digital codes. In early stage of character recognition, so single character recognition was the main focus, and especially many approaches were proposed to Chinese character recognition, which is typical of complex shapes. And many methods of normalization, feature extraction, dimensionality reduction, and classification were proposed. But recently, so the approaches have been dominated by deep learning, which unifies feature extraction and classification, and so superior performance have been achieved. For text line recognition, so there are different approaches. One approach is based on explicit or over-segmentation of characters, and the implicit segmentation approach is to measure sliding windows and and group the study windows into characters. A typical approach is the hidden Markov model, and recently recurrent neural network, particularly the bidirectional LSTM neural network, has been dominating in text recognition, and the BLSTM has been combined with the convolutional neural network so as to extract more powerful feature from images. And a sliding window classifier. So this is based on actually character classification is quite flexible to localize and recognize characters in text line imaging. The RNN-based approach, especially LSTM, was proposed in 2006, first for speech recognition and then extended to text recognition. So it since it reported superior performance on English handwriting recognition, and since then it has been dominating in text recognition. And recently, so it has been combined with convolutional neural network for visual feature extraction. So the oversegmentation-based approach is still competitive, particularly for Chinese handwriting recognition, because of the large number of character categories. So in this case, the recurrent neural network is less effective. And the convolutional recurrent neural network, in brief, CNN. So because of the combination of convolutional neural network and recurrent neural network, it has been superior for syntax recognition and also handwriting recognition. The curved or arbitrary shape text recognition has also been studied in recent years. Since the text line is not in linear structure, so attentional network has been very effective for this problem. And typical instance is the Esther approach, using attentional syntax recognizer and use the rectification network for the text line shape rectification. So there are many approaches proposed in recent years, also for end-to-end text detection and recognition, or called text spotting. In traditional approaches, the text detection and recognition were separate, and but now it's shown that the joint training of the text detection model and the recognition model can be beneficial for the performance of both detection and the recognition. So the approach of force is an early example, and a recent approach called Text Dragon is based on local region detection. So it can be viewed as a character-based detection and the recognition approach. So in this case, a sliding window classifier is used for text recognition, so that it can be quite flexible to deal with the arbitrary shape text. And so the recent text spotter v3 used a segmentation proposal network to segment the text regions for arbitrary shape text spotting. And ABC is yet a new attempt. So let's see. Based on so many deep learning based approaches, so what performance have been achieved? So for layout and analysis, there are many public data sets. Some of the recent data sets include handwritten regions like the RAID BAD data set. The DIVA data set has a small number of images, but with pixel level annotation. The Mao data set has multilingual documented images and a large number of documented images mixed with printed and handwritten texts. So these are two examples of the images. So here are some typical examples, results using full convolution neural network for text line segmentation. On the ICPRAI data set, we can see that a high accuracy of as 97% can be achieved using full convolution neural networks. And on a small data set of DIVA, data set with the pixel level annotation, fully neural networks with multitask training can achieve high accuracies for page segmentation, text line segmentation, and baseline detection. But this approach heavily depends on the availability of pixel level annotation. And some more approach based on a fully convolution neural network have also achieved good performance on the model data set, but still this data set looks to be quite challenging. For handwriting recognition, there are many public data sets, including the English data set IAM and French handwriting data set REMAS. So these are some typical results. So when the lexicon is not used, so we can see that the word level error rate and the character error rate are still appreciable, but using lexicon, the error rate can be reduced largely. For Chinese handwriting, so we released a large data set called Cassia, including both segmented characters and also handwritten pages. For both online character recognition and offline character recognition, recent approaches have reported high accuracies as 98% for online character recognition and 97% for offline character recognition. And for page recognition, so many approaches are now based on text line segmentation. And the performance is measured by character level, correct rate, and accurate rate. For offline text line recognition, so recent approaches have achieved character rate of over 96%. And for online, so the correct rate is a little higher. And syntax detection and recognition and are hot topics in recent years, and many data sets and many approaches have been proposed. So the performance is measured by word or line level recall, precision, and F measure. So these are some images of the data sets of ICTA 2013 and ICTA 2015. So this is a typical data set of arbitrary orientation text. And these are arbitrary shape text data sets, total text and CTW 1500. So these are some recent results of multi-oriented text detection. So we can see that on the data set of ICTA 2015, the F measure can be as high as 90%, and on the challenging data set of ICTA 27 MLT, the F measure is now as high as 80%. For arbitrary shape text detection, so the F measure is also quite high, as 88%. For syntax recognition, so there are some public data sets, but all the data sets are quite small. For example, the IIIT data set has only 3,000 test images of words. And now many approaches can achieve quite high accuracy. So even without the lexicon, the about 94% correct rate can be achieved on the regular data sets, and on curved data text, the accuracy is also over 90%, and some data sets have accuracy of 87%. For end-to-end detection and recognition, recent approaches has shown that the end-to-end recognition can be also beneficial to improve the performance of detection, and the end-to-end recognition rate, of course, is lower than that of text recognition provided correct location. And these are end-to-end recognition results for arbitrary shape text recognition. There we can see that the recognition rates are much lower than oriented text. So we can so we see that many approaches, especially the recent approaches based on deep neural networks, have achieved superior performance. So we can summarize that. So in the past 10 years, especially for text recognition, the approaches based on LSTM plus CTC have been dominating, and deep learning-based approaches have been dominating both computer vision and document analysis since 2012 because of the superior performance of ANXNet in large-scale image classification challenging ImageNet. By end-to-end training, so now deep neural networks can achieve high performance in different tasks, including layout analysis, text detection, and recognition. So these tasks have been, the performance have been improved largely compared to the traditional approaches. But however, the traditional approaches, for example, those based on over-segmentation, use conditional random field or HMM, are still effective when combining with the deep neural networks. So in this case, the deep neural networks are used to extract visual features, and the traditional models used to model the structure of the text. And we can see that the deep learning approaches actually largely relies on large data set with labels. But in many applications, however, the label data is somewhat limited. So in future research, semi-supervised learning and weakly supervised learning for document analysis should be the main focus. And so it's shown that for some tasks, the performance are now reaching the roof, especially for regular handwriting and some syntax data sets of small scale. However, so these data sets have been well annotated. So here are some new trends in document analysis. So now, so we are dealing with more and more complex layout images with more types of elements, and some new data sets are released in recent years, and full-page text recognition. So this is useful when it is hard to segment text lines, and also human segmentation of text lines is quite laborious, and sometimes the automatic segmentation of text lines may prone to errors. So the full-page text recognition has been attempted in recent years. And in addition to text, so other elements in the document images like tables, mathematics, graphics, signature are also very important, that they are redrawing attention in recent years. And the recent works show that the table recognition and the mathematics recognition are still challenging, and the best results are still insufficient. For example, in recent works, the best result of handwritten mathematical expressions recognition has full expression accuracy of less than 60%. The language information has been integrated more closely in document analysis, in traditional approach of text recognition, so language model has played important information, but the language model and text recognition model were trained separately. And recently, it's shown that the joint training of document recognition model and the linguistic model can be beneficial. For example, in text recognition and also in layout analysis, the text information can be used to categorize the text regions into semantic classes and also improve the region segmentation accuracy. And a recent work called a layout LM, modeling the interactions between text and layout information using a deep neural network. So text VQA is now also drawing attention in document analysis community. So despite the great progress benefited by deep learning approaches, we can see that there are still many remaining problems. So let's review the objectives of document analysis. One objective is to digitize document images. So even though the accuracy has been improved largely, but it's still not perfect. So there are still some remaining errors. And all the deep learning approach relies on labeled training data set and a large data set heavily. So this is not realistic in some application scenarios. And there are many long-tailed or imbalanced problems, like in historical Chinese documents. So the number of character classes can be more than 100,000 classes, and many classes has no labeled samples. And multilingual text recognition and the domain shift are also not solved a problem. And in the so-called end-to-end deep model usually has poor explanation and reliability. For example, they can be sensitive to noise and outlier. And for semantic information extraction, now the integration of linguistic model and text recognition model is still not fully explored. So this is an example of text recognition. Even though the deep neural network has performed very well, there are still some remaining errors. So it was hoped that the recognition errors or low confidence characters can be detected and automatically, but this usually cannot be done very well by deep neural networks. But instead, traditional recognition methods may perform better for this purpose. For future research, so we can, in sense of fundamental theory and methodologies, there are many research issues like the learning for small or imbalanced data and weakly labeled data, transfer learning and domain adaptation, online learning adaptation, few shot learning, zero shot learning, and the model explainability, reliability, and confidence estimation, and the document interaction include the interaction mode and the learning with human in the loop. So these basic issues are very important for document analysis and recognition. And in respect of textile recognition, so the current recurrent neural networks actually do not have good explainability. So the explainable sequence model should be studied in the future, and the linguistic modeling and the fusion and the joint training of linguistic model and text recognition model, and the adaptation of language model, and the multilingual documents, especially those documents with mixed languages, full-page recognition and semantic information extraction. So these are have been actually fully explored. And for document image level, so the So the development of new capturing device can be very useful, and the complex layout analysis and the logic structure are still remaining issues. And the joint model for layout analysis, text recognition, and information extraction can be very useful. And from the viewpoint of application, we can find some more research problems. For example, the recognition of objects beyond text, including mathematics, tables, symbols, diagrams, stamp, and signature, and the reconstruction of document layout, document authentication, and the right identification, and the interpretation of character structure. And many new applications can be explored, like human interface based on documents, the robotics, archaeology, education, travel aid, impaired person assistance, etc. So in summary, so there are still many research issues, and we have many challenges and opportunities for future research of document analysis and recognition. Thank you very much.
Thank you, Professor Liu.
Thank you.
Thank you for a very comprehensive analysis, and also look into the future and the new frontiers in document analysis and recognition. And we are very happy that we have our keynote speakers this morning, and we appreciate very much also the presentations of various papers.
The Q&A, what if document involves handwritings, such handwriting Chinese characters?
Yes, actually, as shown in my slides, actually, so current, so we are now concerned with both printed documents and handwritten documents, and some documents even have mixed printed text and handwritten text. So of course, so handwriting is the main focus of document analysis, and now so the current approaches can deal with handwriting very well, actually. So let me directly move on to the next question. So on online or offline, if the online handwriting has the trajectory information of the stroke order, so usually, if we can utilize the trajectory information well, so usually online recognition should be able to give higher accuracy. So this is actually verified by some of previous experimental results, actually. Well, original Chinese handwriting style not, so this means traditional Chinese character. Actually, traditional Chinese character has a more complex structure than simplified Chinese character, since they have more strokes. Actually, the complex structure actually is beneficial for character recognition because they have richer shape information. So the traditional Chinese character recognition is, the complex structure is not a problem, but the large number of categories is a problem. Since for traditional Chinese character, the number of categories may be as large as 100,000 categories, but for in modern language, so usually the number of commonly used characters is only about 10,000. And then the final question, DCN apply to right identification. DCN means convolutional neural network. Of course, actually it has been used in right identification and signature verification. So the convolutional neural network is used for feature extraction, and then a distance metric is trained, for example, using CMIS network to train the a binary classifier for signature verification.
Before we end, I would like to point out that for the final day, October 23rd, on Friday, we'll have the closing ceremony, apart from a technical session on forensic studies. In the closing ceremony, there will be awards and also promotion of 2022 in Paris, and also the choice of 2024. Now we have a proposal from Korea. And apart from that, we have the concert, very, very exciting one. And it's my many years of experience that I have collected such a program. And you will hear singers like Pavarotti, Celine Dion, Elvis Presley, Oriental Elvis Presley, and other famous Chinese singers like Bai Guan and so on. You can find the program now and the names of the songs under registration. So in our website, if you click registration, you will find the content of the concert program. So thank you again, and this is the end of our session today, and we'll see you tomorrow. Thank you very much.
Okay, see you tomorrow.